Yeah, so I'm Christiaan Bekker from here at Watt University. I'm a research fellow there with the Royal Academy of Engineering. But my alma mater is at the University of Queensland here, so there's that Australian connection. I've been really excited to see the quantum developments over the last few years here. So my talk's going to take on a bit of a different tack. So instead of thinking of quantum effects in light harvesting, thinking of how we harvest light from quantum emitters more effectively and efficiently, and that kind of element of how efficient we want to make our quantum systems for future sustainability goals. Um, Before I get into my talk, let's just see if this works. There we go. I just wanted to say thank you to all the contributors of this work. In particular, I want to mention Professor Christiaan Bekker, whose group I was a postdoc in for some of this work, and our collaborators in Oxford, who we'll talk about a little bit later, who are experts in laser writing. So, to give a bit of context for where I'm going, I want to talk a bit about quantum communication networks as one of the large kind of fields of application that we can see quantum technologies going towards in the next few years, maybe decade, where we want to think about quantum secure communication network. We can also think of these kind of capitalizing on current telecommunications fiber infrastructure, so actually using photons to share our quantum information. Now, this picture is from the Quantum Internet Alliance in Europe, but there's really a whole load of different networks like this popping up all over the world where we want to at least start learning on a smaller scale how we can share quantum information, quantum secure keys, but eventually try and send this all over the world. And there are some really interesting things you can do with it, like encryption, or I like the idea of blind quantum computing, where you can actually send your quantum states to distributed quantum computers, and they can calculate your process without actually knowing what they're calculating. So these are really exciting, I think, applications for us. But one of the problems of using optical fibers for communication, as one of our options, is that in-fiber loss means that we are very much limited to the distances that we can travel between nodes before we just lose our quantum information, our quantum states. And so if you have a few hundred kilometers, that's fine in Europe. But say in Australia, you're not going to get very far with a few hundred kilometers. So we really want to think, how can we get further without having to trust nodes in between? And so here we come back to the idea of quantum repeaters. So the fact that we can't amplify our quantum states like we can amplify our classical optical signals that we're sending it through the internet. So we really have to have think about these quantum repeater stations where we can distribute entanglements and send entangled particles from subparts of our connection, so nodes between the two ends we want to send them to. And in this way, we only have to send our quantum states a part of the way, and we get polynomial instead of exponential decay of our states, and we can get further. And so, but one of the key elements of these quantum repeater stations, once we make them, is that we need quantum memories. We need some way to store our information while we're waiting for entangled particles to move around and to then access that information with high efficiency later, so we can do a projective measurement and distribute our entanglement. So this also then means, quantum repeaters means quantum memories. And one of the classes of these quantum memories that I want to talk to you about are solid state point defects that are based on atomic vacancies or impurities. So it depends if you want to remove atoms or add different elements into your material. And these can work as quantum memories because you can have single photon emission from them, so you can actually interface with your flying photonic qubits, and you can encode information onto the spins, so electron spins trapped by these solid state point defects, and so you have solid state quantum memories. Silicon carbide is a very exciting and interesting potential material for this for several reasons, among them being that it's good to it's much easier to fabricate than some other platforms. Another exciting, I guess, property of it is that there are many different types of spin defects that you can use in the material that span a large wavelength ranges. You can kind of choose what you want, what platform, what material, what defect you use based on your application. So I'm going to talk about about silicon vacancies, just to mention this here, in this talk, which operated about 1,000, just under 1,000 nanometers wavelength. But I also just wanted to mention there are also directly telecom communication emitters like vanadium, of which we've recently published a paper, which is exciting, but I'm not going to talk about it. It's actually it's accepted in Nature Communications now. Yeah. Yeah. One of the key problems for any of these defects is that our performance is limited by the efficiency of our control and by the capability we have to scale these defects to large arrays. You can think if you just say, oh, let's look at a crystal, let's make emitters randomly in them, and then find out where they are, it's going to be very difficult to move from 1 or 10 quantum memory nodes to thousands, or maybe one day millions if you want to talk gigabit memories, right? So the vision that I have that we're working on at Herit is this idea of a scalable and integrated, so which here also means efficient quantum memory node that's based on solid state spin cube using silicon carbide. So I also want to really emphasize this need for efficiency, in the sense that, as we've heard, if we want to be sustainable, we really need to think early on, while we are developing our 1 to 10 bit systems, how is the energy cost we're going to require for these going to scale when we get to millions of bits that we want to use eventually, right? So I had 4 components. I'm not going to talk about all of them. The main thing I want to talk about today is spin light interfacing. So how do we efficiently harvest light, couple light in, couple light out of these solid state defects? And I'll mention a little bit of deterministic spin creation, the fact that we need to actually place our quantum memories reproducibly at least in space, right? Yeah. So the element of enhancing our coupling, so enhancing the light we can get out of our emitter, really for us comes down to these solid immersion lenses. And the fundamental operation principle is just the fact that when you have an emitter sitting in silicon carbide or any other high refractive index material, you get most of your light reflected back into the crystal. So you might excite your quantum memory, try to extract the light back out again to send onto your entanglement distribution, your measurement. But if like any light that goes off to a large enough angle just gets reflected, your efficiency is going to be very low for your quantum memory. And so for a solid immersion lens, just the very basic idea of a hemispherical lens, you say, okay, as your light comes out, any light that travels up hits my interface at a normal incidence, and so we minimize reflection and we enhance the brightness of our emitters just by enhancing how much light actually gets out from the crystal. It's somewhat of a simple idea. There's actually some more we can do with this if you had more control, where you can decide where you want your light to go, so you can actually angle it up and collect it more efficiently. But that's kind of the next step. And in all of this, our main cost is device complexity. We now have to build a component on top of our emitter. We can't just look at them in a crystal, right? But we can deal with that, right? Especially when you're a quantum engineer, you say, we want to make these devices, we want to actually improve our devices by thinking about things cleverly. I should actually say here, don't worry too much about all these different methods. All I actually want to say here is there are 2 different ways in which people make lenses at the moment, or 2 different types of process. I say and then contradict myself, but on the one side, typically people have scalable and low-cost methods where you can create lots of lenses, but where you don't have very good shape control. On the other hand, you can have very high precision, things like 2-photon polarization, focus ion beam milling, where you can make your lens exactly as you like, but they are very slow, very time-consuming. And both of these don't give us all the capability that we need. Now, in our research, we've been looking at a kind of intermediate process between these 2 that's emerging, which is this idea of grayscale lithography, where you do a photolithographic process, which normally means I have a mask, I create some patterns in my mask, and then I etch that down to create my structure. Normally, you just say, I want to resist here, I do not want to resist here, but you can go the next step and add a bit more complexity to your design and say, I want this much of my mask remaining at these positions, right? In this way, we can make shaped structures again, at the main cost of design complexity. But this gives us, if we're already committed to adding out a sophisticated device, a way to get both scalable and low-cost manufacturing, where we can make many devices in one run with shape control and precision that at least starts getting closer to focus on beam milling or those kind of precise processes. This is a very promising process. One of the problems with silicon carbide is that silicon carbide is very hard. And it is very difficult to work with these specific resistors because we are kind of limiting ourselves to a particular process to be able to reach high aspect ratios in our devices. So this is one limiting factor we found, that no matter how much we optimize our process, we could never get to a hemispherical solid immersion lens. We only have relatively shallow ones. So one exciting development that we'd made is this next step of actually having a two-step etching process in silicon carbide to be able to make hemispherical devices. And this is the paper. This is backwards. This is the work in the paper that I wanted to discuss. So what we wanted to do was add what we call a grayscale hard mask to our lithography protocol. So normally when you do photolithography, so if you want to make a device I was mentioning before, we have our resist and we go straight from this and imprint our shape into our substrate. By adding, in this case, a separate material, we actually decouple. We create two etch steps. So we imprint our resist into our hard mask, in this case glass, and then so imprint that into glass, then imprint the glass into silicon carbide. And by having two etch steps, we do more than just add complication to our system. We actually give ourselves the ability to separate the two processes, the process of working with our resist and working with our substrate, in terms of chemistries, in terms of etch process, in terms of difficulty to etch. I should also mention that we use reactive ion etching, just in passing, so a dry etch method that's anisotropic, so etches straight down. And we also give ourselves the possibility of tuning and selecting, for example, how selective our etch is. So how high do we want our final shapes to be? Almost like after the point of developing our resist and creating our shapes. So this has been really helpful for us in that we could then add this extra little bit of capability to reach hemispherical or aspect ratios for our devices, and do them with a very scalable approach. So as you can see here, we've just got a little subset here of a chip which we made. There's 20,000 or something cells in the whole chip. This is just a subset. And then we could then make with nice aspect ratios. So as I said, our goal here is to take out our solid state emitters in silicon carbide and make them brighter using these lenses. So firstly, I want to just point out the shape control that we could have, so we could show lenses going from more conical to kind of super hemispherical shapes, or for example, have these. I haven't talked much about trenches, but you can think about directing light that's going off the side up, so you can have different shapes for like trenches on the sides. There's a lot of tunability and a lot of thinking on how do we make optimal devices that's still in its very early stages, but they were really excited by the capability. And this is the limitation of what we could get, like the best aspect ratio without having that what we call grayscale hard mask. So then we took these devices. We initially have just shot electrons at the whole chip, and this is so shooting high energy electrons. We create individual vacancies, so we create silicon vacancies, and these are the emitters which we're studying in this particular case. These emitters, as I say, you pump them with red light, and then they emit in infrared, and so we can look around at photoluminescence from these. And so on the right here, this is just in the box. It's just a reference to a little bit of the sample where we can see all these different spots. And some of the bright spots here are actually two silicon vacancies nearby each other. Some of the darker spots are single vacancies where you've just knocked away a silicon atom. This here is our the same photoluminescence map inside of a solid immersion lens. You can see these four images here that come up brightly, or more brightly at least, because they're inside the lens. So here is just an example of what we call pass saturation plot. Just as you pump your your emitter, it has this saturating behavior, as it's only able to absorb and emit light at a certain rate. And here you can just see that basically the amount of light we collect from an emitter inside a cell is enhanced. There are two elements that I should mention here. So this curve here follows this equation, and there are two elements of enhancement. One is the fact that our saturated brightness is higher because we now enhance the amount of light that can leave the crystal. The other element of this that I haven't talked too much is the fact that because we are shining our light through a lens, we make our spot, our excitation spot on the emitter smaller. So we also start saturating earlier. And that's this kind of power intensification here. And so we did statistics and looked at several of these, about 40, I think, in total between the solid immersion lenses and the bulk, and we could compare how much brighter they are. And so we've got about a factor of 4 at the moment in enhancement. Thanks. So that was very exciting for us that we've made our first steps towards this, trying to make our devices as bright as we can. Where we want to end up with this at cold temperatures is that we want to get to a regime called single shot readout regime, where you can just effectively do one query of your quantum memory and get out what the state is, because then that's what you want to do when you're doing entanglement distribution. We're not quite there yet, but there's still that's what we're aiming at. Another point I just want to quickly mention here was that at the moment we had just randomly made emitters everywhere, and what we really want to do is make these emitters deterministically, at least deterministic in position. We're always going to have Poisson noise effects or statistics to deal with. And so what we are working with Oxford, who collaborators there who are experts at laser writing of solid state defects, is using a femtosecond laser and basically focusing that on a point and trying to create enough damage to actually just dislodge one silicon atom from that region which they're writing, so you can end up with one emitter in the center of your lens. And this way you get the optimal position for your solar immersion lens, and you just get that both the extra positioning, the extra enhancement from deterministic positioning, and the ability to choose where you want your memories to be, so you can make arrays of them. So that is my talk. I hope it's been interesting. Just a quick summary is that the grayscale hard mask fabrication protocol I was presenting gives us a way to do scalable, shape controlled, and high aspect ratio microstructures in silicon carbide. Some initial lenses we fabricated with this method show enhancement of up to 4.4 brightness and 3.8 intensification of the laser spot, and gives us a way to improve our performance. And then we're also working on optimizing the light harvesting by choosing where our emitters are. And we can extend this beyond microlenses and materials beyond silicon carbide. That's all exciting because we've got that process. But yeah, that's more work to be done. Thank you very much. Any questions?
Are there any questions from the audience?
Just wondering about the prospect of AR coatings, given the very large range of aspect ratios that you would need to come up on, but on the other hand, silicon carbide's index, if I recall, is quite high.
Yes.
Which is why you're doing this in the first place.
Yes. So silicon carbide's index is 2.6 refractive index, so it's quite high. I think there is potential for AR coatings, definitely. So in diamond with focused ion beam milling, the groups, so I think Ronald Hansen's group in Delft, have shown that you can get an enhancement of about a factor of 10 without an AR coating, and then adding an AR coating you get up to 20, so another factor of 2 or so better. So you can definitely do that, and that would be definitely a good option to pursue.